Check it out now, y'all.
nanoHUB-U online instruction.
Hello and welcome back to nanoHUB-U's Introduction to Bioelectricity. This is lecture 5, our fifth and final lecture in week 3. This week we've been talking about models of biological conductors. So we began in week 1 by talking about an overview of the nervous system and simple circuits in the nervous system. In week 2, we dove a little bit deeper into the cells. We looked at ion channels. We looked at neurotransmitters. We looked at the way they're synthesized and they're released and they're reuptaken. We looked at different drugs and how they affect that process and the postsynaptic potential. And we talked about what an action potential is and the resting membrane potential as well. Then we started to look at the models, and this week we started to look at the models that have been developed to describe the electrical behavior in cells and how those models account for various processes and which sorts of processes they do not account for. We began in the first lecture of this week by looking at electrically large and electrically small cells. We went on to develop the core conductor model, which describes the relationship between membrane currents and voltages inside and outside of the cell. Then we talked about the equivalent circuit for the membrane, and we developed the cable model and the cable equation to describe currents and voltages in a cell during passive current flow conditions, so when there are no action potentials. And we came up with a cable equation, and we talked about how there were 2 solution types. There were the time-independent solutions, where the membrane voltage is not allowed to vary with time. It's clamped. And then there's the time-independent solution, when the membrane voltage is allowed to vary. It's not clamped. So today, in this lecture, lecture 3.5, we're going to talk about the time-dependent solution of the cable equation, which is of this form, but we'll get there. All right. So, to recap, there are 2 modes of solving the cable equation, the time-independent and the time-dependent, and the difference is whether or not we allow the membrane voltage to vary or not. If it doesn't vary, then the derivative is equal to 0, and the equation simplifies, and it's fairly straightforward to solve by assuming an exponential solution, as we did in lecture 3.4. More interestingly, the membrane voltage is allowed to vary, and that allows us to begin to ask interesting questions and model phenomena in which you have temporal and spatial summation at the axon hillock of postsynaptic potentials that can be excitatory or inhibitory at any number of different synaptic locations in the dendrites or in the soma. And that's what we're going to look at today. So for the time-independent solution, assume that our stimulus, Ke, is equal to the impulse function. So Ke, which we've been setting to 0 most of the time, we're now going to leave not 0. So Ke is going to be equal to some current, i.e. as a function of time, and that current is going to be equal some amount of charge, Qe, a total charge that's going to be delivered, and that total charge is going to be delivered at an instant in time. All of it at an instant in time. And so the way we model that mathematically is using the impulse function delta t. And the impulse function gives you an infinite area over an infinitesimally small space of time. So if you integrate the impulse function over all time, you get 1. And if you multiply that 1 times the total amount of charge delivered, you get the total amount of charge that you want in your current. So Qe is the total amount of charge delivered, and if we plot Ke, we find that the entirety of that charge is contained in the area underneath the curve of this infinitely tall pulse that's infinitesimally small in width. Okay, so in this case, we can take the second integral of the membrane current that's applied, the electrode current that's applied per unit length. So Ke is equal to Qe times the impulse function, and the impulse function is over space and time, and it has a value at space equals 0, z equals 0, time equals 0. So if we integrate it over all z and over all t, we end up with just the total charge Qe. Let us also define normalized variables. So we've talked about lambda, the space constant, we've talked about tau, the time constant. Let's normalize distance and space with those constants so that lambda prime will be equal to z over lambda and tau prime will be equal to t over tau. And if we do that, then the membrane voltage, which is a function of z and t, can be described as the membrane voltage as a function of lambda prime lambda and tau prime tau, because lambda prime lambda is z over lambda times lambda, which is just z. and tau prime tau is tau over tau, which is 1 times t is just t. So this is exactly the same thing. But if we write it in this fashion, then we can say that because lambda and tau are constants, a function of a constant isn't really a function at all, we can drop those and we can say that the membrane voltage Vm prime is a function of lambda prime and tau prime. And that becomes useful in helping us to solve the equation. So bear with me. Similarly, Ke, the current that we're applying with the electrode as a function of Z and T, can be expressed in terms of Ke prime as a function of lambda prime and tau prime, which is equal to, don't forget, it's equal to the total charge QE divided by lambda times tau, and all of that multiplied times this impulse function. Okay, so we have those two variables redefined. Now we can rewrite the cable equation so that it takes into account these new values. So the cable equation that we had before can be rewritten as the second derivative of the membrane voltage, but Vm prime now, because it's a function of lambda prime and tau prime, with respect to lambda prime squared, is equal to Vm prime as a function of lambda prime and tau prime, plus the first derivative of Vm prime as a function of lambda prime and tau prime with respect to tau prime now, minus QE divided by lambda tau times the impulse function as a function of lambda prime and tau prime. And this is equation 2. So you can recognize the capacitive current element, the resistive current element, where we've moved the lambdas over, but we've now eliminated the lambdas because we've replaced them with these normalized variables. So we've gotten rid of the constant out front of the second derivative of the membrane voltage, and that's what we're after. And finally, we can define a new variable, W sub m. And W sub m is going to be a function of lambda prime and tau prime. And we're going to say that W is equal to Vm prime times e to the tau prime. And when we're defining a variable, students sometimes look at that and say, well how do you know that that's true? When you're defining a variable, you can define it any way you want to. You can make up any variable you want. Whether it's useful to make up the variable, that's another matter. But if you follow with me, you'll see that this definition is quite useful. And so mathematicians come up with these definitions in order to simplify complex mathematical problems into a form that they recognize because it has already been solved. And then they can apply known solutions to unknown problems and solve them by inspection, which is what we're trying to do here. So for now, bear with me, we're going to define W sub m as Vm prime e to the tau prime. Noting that the second derivative of W sub m is going to be equal to the second derivative of the membrane voltage times the second derivative of e to the tau prime. And when you do that with respect to lambda, it's going to change nothing at all because e to the tau doesn't vary with lambda. So the derivative of it will be 0. So it'll be the derivative of this times that plus the derivative of this times that. If you'll recall from your calculus terms, derivative of AB is equal to A derivative of B plus B derivative of A. But the derivative of e to the tau is 0, so that term disappears. Similarly, we can do the derivative of W sub m with respect to tau, and now e to the tau is a function of tau, and so you will get a derivative term, so you will get A derivative of B plus B derivative of A. And that means that you have A derivative of B is Vm prime e to the tau, or V prime m e to the tau, plus this first derivative of Vm prime, it's derivative of A times B, multiplied times B, e to the tau prime. So from your freshman year calculus, the derivative of this term is equivalent to that in terms of the membrane voltage. And you can begin to see why we've defined W sub m the way that we have. The second derivative is going to be nothing more than the second derivative of the membrane voltage, but the first derivative creates a first derivative term and a 0th order derivative term. And we can do this to now substitute equations 3 and 4 back into the cable equation, such that 1 over e to the tau prime times the second derivative of the membrane, or W sub m, will be equal to 1 over e to the tau prime times the first derivative of W sub m with respect to tau, instead of lambda, minus this added current term. So we've taken the equation that had the second derivative of the membrane voltage, the first derivative of the membrane voltage, and the 0th order derivative of the membrane voltage, and replaced it with an equation that has the second derivative of W and a first derivative of W, and that's it. If we set QE, the charge delivered to 0, as we've done it again and again, this term zeroes out, and the equation reduces to the second derivative of W with respect to lambda prime is equal to the first derivative of W with respect to tau prime. And that is of the form of the homogeneous diffusion equation. So this is exactly what we were after. We're trying to take a complex mathematical equation that we don't know how to solve and put it in the form of an equation that is of a known solution, in this case, the homogeneous diffusion equation, so that we can then take the solution to the homogeneous diffusion equation and plug it in and solve by inspection. And so we're going to be able to solve the second derivative of W sub m with respect to lambda prime squared is equal to the first derivative of W sub m with respect to tau prime by inspection. And by inspection, we know that W sub m, therefore, must equal some constant A divided by the square root of 4 times pi times tau prime e to the minus lambda prime squared divided by 4 tau prime, again by inspection. And if you want to see exactly how you get to this solution, you can look up the solution to the homogeneous diffusion equation. But for the purposes of this class, it's sufficient to know that it has been solved, that we've been able to express the cable equation in those terms, and then solve the cable equation. But actually, we haven't solved the cable equation yet. We've solved for W, and W doesn't mean anything. It's a variable we made up. But we do know how it relates to Vm, because that's what we're trying to really get after, is the membrane voltage. And W is related to Vm because W and Vm are related by that e to the tau. So we can substitute back in and say that V prime m is equal to A over the square root of 4 pi tau prime, e to the minus lambda squared over 4 tau prime, and 1 over e to the tau. Right? Because we're bringing that e to the tau back in. We're getting rid of the W. And so 1 over e to the tau is the same as e to the minus tau. And so we have this e to the minus tau or tau prime in the solution. But here we're still solving in terms of lambda prime and tau prime. And we don't really work in a world of lambdas and taus. We work in a world with meters and seconds. So we want to get back to z and t. And so we reverse that substitution as well to find that the membrane voltage as a function of z and t as a function of space and time is equal to some constant A divided by the square root of 4 times pi times t over tau multiplied times e raised to the z over lambda squared divided by 4t over tau, and then all of that multiplied by e to the minus t over tau. And that is the solution, the time-dependent solution to the cable equation. And now we need to find A. To find A, we can rearrange that equation as follows. We can rearrange our equation 5 as follows. We can say the second derivative of W sub m with respect to lambda squared is equal to the first derivative minus this current term. And now we're not going to zero out this current term. We're going to integrate with respect to lambda. And when we integrate with respect to lambda, we're going to say integrate each term on both sides of the equation from minus infinity to infinity with respect to lambda. So you're going to take the integral from minus infinity to infinity of the second derivative of W sub m is equal to the integral from minus infinity to infinity of lambda here with respect to lambda of the first derivative of W sub m with respect to time minus lambda rho QE over tau. This comes out because it's all a constant times the integral from minus infinity to infinity of the impulse function multiplied times e to the tau prime. Okay, now the left-hand term in this equation, this term here will go to 0. This term in here remains, and it gets passed down. And then this term, the negative constant times the integral, remains, and it moves down as well. The constant is here, the minus sign goes away because we moved it to the other side of the equation, and the integral of the impulse function over all lambda is equal to the impulse function now as a function of tau, because we've cleared away the lambda variable by integrating over all lambda. And so the only question left for us in this simplification is what happened to this term. And to get at what happened to this term, You can think of it intuitively. Intuitively, remember in lecture 3.3, we plotted the membrane voltage. And then we said, look, the current outside the cell is equal to the first derivative of the membrane voltage. And the membrane current is equal to the second derivative of the membrane voltage. The second derivative of the membrane voltage, here. And we plotted it by inspection, and we showed that at times you had a current flowing in, at a time you had a current flowing out, and when the current's flowing into the cell, it's depolarizing it. When the current's flowing out of the cell, it's repolarizing it. But what's important to note is that when you're looking at the membrane current, which is proportional to the second derivative, your starting resting potential of minus 65 millivolts is the same as your ending resting potential of minus 65 millivolts. So whatever current flows into the cell when you're depolarizing has to equal the total amount of current flowing out of the cell as you're repolarizing. So the total charge in has to equal the total charge out because the ending voltage is the same as the starting voltage. So the membrane current, the integral of the membrane current, the integral of the second derivative of the membrane voltage has to be 0 because the membrane voltage at the end of the action potential is the same as the membrane voltage at the beginning of the action potential. So as long as our membrane voltage remains constant over long periods of time, small fluctuations in postsynaptic potentials aren't going to change the fact that the average current is 0. And so that's why this term goes to 0. And you're left with the integral of the first derivative is equal to, as we move this to the other side of the equation, the impulse function integrated over lambda, which just takes out the lambda term. So it's the impulse function times our constant. And that we can solve. So we can rearrange the order of integration so that instead of taking the integral of the derivative, we take the derivative of the integral. And we can say, now we're going to say that the derivative with respect to tau prime of the integral of W sub m with respect to lambda is equal to lambda RO QE over tau multiplied times this impulse function as a function of tau prime. And the derivative with respect to tau of the integral of W is equal to the derivative with respect to tau of the integral of what we've already solved. We already solved W. And it includes a constant, some variable terms, and the constant A that we're trying to find. And all of that, of course, can be expressed in terms of the derivative with respect to tau of some constant A times the step function. And the derivative of the step function is the impulse function, and the impulse function cancels out, and that gives you A equal to lambda RO QE over tau, and the impulse function, which is canceled out. So we've now solved for A. We know that A is equal to lambda RO QE divided by tau. So it's the space constant, the time constant, the resistance per unit length outside the cell, and the total amount of charge delivered. And since we know the total amount of charge delivered, we know what A is. And we can plug equation 7 back into equation 6 and find our time-dependent solution of the cable equation, which says that the membrane voltage as a function of Z, the space, and T, time, is equal to a constant, lambda, the space constant, times RO, the resistance outside the cell per unit length, times QE, the total amount of charge delivered when we stimulated, divided by tau, the space constant, divided by the square root of 4 pi times the time t divided by tau, the space constant. So t is the only thing in this term that is not constant. Multiply it times the exponent e to the z over lambda squared divided by 4t over tau, and then multiply it times e to the minus t over tau. And so if you have a point, we'll describe it as the origin, and we plot it in 3 dimensions with a membrane voltage in the z-axis, the lambda distance in terms of lambda number of space constants in the x-axis, and the time constant tau, number of time constants that you moved out in time in the y-axis. So you have x-axis is space, y-axis is time, z-axis is membrane voltage. At the origin, you're going to have some membrane voltage. Then, as time goes by, you're going to move down the x-axis and you're going to roll off. So that after 1 lambda, you're going to have dropped off by 1 over lambda squared. After 1 time t equals tau, you're going to have dropped off by e to the minus t equals tau. Now tau over tau is e to the minus 1. So you'll have dropped off by 1 over e after you've gone tau in time. And you can see this exponential relationship both in space and in time. And that's just for a single initial postsynaptic potential. If you have a number of different postsynaptic potentials at a number of different places on a neuron, and you know what the distance is to the axon hillock, and you don't care what postsynaptic potentials do as they're flowing in other directions. The only thing you care about is what do postsynaptic potentials do when they're flowing towards the axon hillock, and how do they add when they get there. So if you know what the distance is to the axon hillock, you know how many lambdas away you are, you know how much your postsynaptic potential is going to fall off. And if you know the distance and you know the velocity, you know how long it'll take to get there. And if you know how long it'll take to get there, then you can use this three-dimensional plot to say not just how much time or how much distance, but in between, on the XY plane, where are you as you get to the axon hillock in both space and time? And you can do this for every postsynaptic potential. And so you can accurately, mathematically model temporal and spatial summation and integration at the axon hillock, and you can determine from any given set, I don't care if it's 1,000 or 1,000,000 in a Purkinje cell, any given set of known, and that's the tricky part, is knowing where the synapses are and when they're firing. But for any given set of known postsynaptic potentials, you can determine at what point in time, if any, you're going to cross the threshold voltage. And that's the point at which you're going to get an action potential. That's what the cable equation gives you, and it's very powerful. What it does not give you, and it's also important to remember this always, is that it does not tell you once you get that firing of the action potential, what happens next. And what happens next is that the ion channels begin to open and close. And when they do that, the impedance, Rm, begins to change as a function of membrane voltage and time. And the membrane voltage, remember, is a function of temperature. So it begins to change as a function of a number of different variables. And you have these fluctuating membrane conductances. And that's what we need to capture when we want to look at active signals rather than passive signals. And that's why Hodgkin and Huxley came up with a model and the equation that they came up with in 1952. And that's what we'll talk about in week 4. And I'll see you then.